everyone. I'm Aadirupa. I'm a postdoc researcher at Microsoft Research, New York City, and in this talk I'm going to give a brief summary of preference-based reinforcement learning, or PbRL in short. Before going to the main content, just to give a brief outline of what we are going to discuss today. So we'll start with what is preference-based reinforcement learning, followed by some motivating examples, the formal problem setup of preference-based reinforcement learning, some of the existing work and theoretical results, and finally the limitation of the existing work and the scopes of future directions. So with that, let's proceed to the basics. So what is preference-based learning? Studies have shown that oftentimes it's easier and involves lesser bias to collect information in terms of relative preferences rather than absolute rewards. For example, in a movie recommender systems, the system can ask a user that how much do you rate a movie in a scale of 0 to 10, and on the other hand, we can just show them two movies and say which movie do you like over the other. Studies have shown that oftentimes it's easier to elicit information from the users in the later case because it's simple to answer yes, no, or one or two optional multiple choice questions, and it involves lesser bias and suffers less from no responses. So with that motivation of learning from preferences, just before going to the formal problem definition, we have several applications, not just movie recommender systems. In various recommender systems, this can be implemented. For example, restaurant recommendations, or in search engine optimization, or in crowdsourcing platform, various online learning platforms. Preference-based learning can be implemented, and it has been implemented in the real-world system. This led to the famous formulation of dueling-banded problem in the banded literature, in the online learning literature, which is a symbol framework where suppose there are k arms, and assuming that there is a best arm in the hindsight, the goal of the learner is to figure out this best arm. For example, in a movie of in a pool of movie of 100, if you have a best movie, you want to figure out that movie and recommend that movie to every user so that you get maximum reward once they watch it. It's an online learning framework where you select two arms, and upon selecting two arms, you get to see a noisy comparisons between which arm is preferred over the other. This is provided by the customer or the environment. We assume generally that there is an underlying preference model which can be stochastic or adversarial, from which these preferences are generated. And upon seeing these preferences, the learner is supposed to update their model and go on playing this sequential game until convergence. So assuming there is a best arm in the hindsight, the goal is often to reach to this best arm in terms of some regret minimization or pack best arm identification objective. Now, though this dueling bandits or this preference bandit framework has been hugely studied in the literature for last 2 decades, unfortunately, the reinforcement learning version of preference-based learning has not been studied at all, or it's very sparsely studied. But oftentimes in real-world system, we have seen that preferences can be state-based or depends much on the user context. For example, in an online retail store management, an online chatbot can try to sequentially interact with the user to narrow down the list of preferences to be shown to the user. While the user come for a shopping. For example, they might first ask what you're looking for, and then they will say maybe they're looking for some shoes, and then they will say what kind of shoes, and then they will say specific brands, and then they will narrow down the search preferences. So definitely the learning of preference feedback or prediction, model predictions depends a lot on the state of the user, the time, the demography, the mood. Various contexts can play in the hindsight, which the dueling bandit is unable to capture. More than that, there are other problems with classical reinforcement learning or state-based absolute value reward framework. For example, suppose we are trying to train a robot to walk from point A to point B. Say this is our robot number 1. We have another robot which is doing the same task successfully, and there is a third robot which is also working successfully from A to B. Now it might be very difficult in terms of the absolute reward to say which robot works the best and what is the which robot has how much reward in terms of their working performance. But just from visually it is easy to say that the last robot walks most like the human, and maybe the first robot walks most in a most weird fashion. So one might say that we like the second robot more than the first, and the third robot's performance the best out of all of them. So reward shaping is another problem with classical reward-based learning. And finally, there's also some multi-objective criteria. For example, in recommender systems, there can be various recommender systems, and the system performance can be measured in terms of different metrics. For example, the watch time, the number of clicks, the CTR, the number of likes, comment, duration of engagement, various things. And different recommender systems can perform differently in terms of several performance metrics. It might be very difficult to aggregate the score and say the performance of ith recommender system is some X. But in terms of preference, it might be very easy to say that overall, seeing a trajectory of, say, duration of 30 minutes or 1 hour, we feel like the user engages most comfortably with ith recommender system. So that is performing the best, and then some J recommender system is performing the second best. So giving a performance or relative feedback is always easier. Now, given that we have motivated enough with why a preference-based reinforcement learning framework is useful, let's try to formulate the problem a little more formally, a little more mathematically. So before going to that, we all know, just for our own familiarity with the notations, in classical reinforcement learning, we know that there is an MDP with a state S, number of actions A, reward model R, transition dynamics P, and some initial distribution of the states P0. And in every iteration, the agent takes some action, it lands up in a state, and based on the state action pair, it receives some reward, and it takes some action, it moves to another state, and this game goes in round. Generally, the performance criteria is measured in terms of the cumulative reward of the agent with respect to the best policy in the hindsight. Now, instead of this classical reward-based reinforcement learning, now if we try to formulate the preference-based reinforcement learning, we might say that now instead of seeing the reward, at each iteration, the agent might have to take 2 actions instead of 1, and upon which it gets to see some preference indicating which action is preferred over the other. So say they take 2 actions, 81 and 82, and this can be just some 2 actions or trajectory or multi-step state action pairs depending on the requirement of the system. And there is also a preference modeling which needs to be done, that we denote by a Chi function. There can be several ways to model this preference function Chi. One way to model it is just assuming there is actually a true reward model in the hindsight. The Chi can be just proportional to the reward difference of the underlying trajectories of the underlying actions the agents have taken. But there can be several other modeling. I mean, the preference modeling can be done even without assuming any underlying reward model, and we'll see in the later slides what has been done in the recent works. Now, so given this is a framework of preference-based reinforcement learning, this can be a formal problem definition. This has been studied very sparsely in the literature, as I mentioned, and though there has been some recent work, they were predominantly applied in nature, and there has not been much theoretical guarantees in terms of the performance of the algorithms. Only recently, Su et al. And Zhu et al. Has proposed 2 reinforcement learning algorithms, which some finite time regret guarantees or sample complexity guarantees. And the rest of the talk will quickly go over the results, the theoretical results, the 2 theoretical results that I mentioned in the last 2 references. So let's start with the result by Su et al. As I mentioned earlier, there is an underlying MDP model, and suppose at each iteration the agent is supposed to take an h-length trajectory. Say at step I or iteration I, it takes two trajectories, tau I1 and tau I2, and the preference tau I1 given tau I2 is modeled in terms of some underlying link function g, which actually maps it such that the preferences of the trajectories are proportional to their underlying rewards. So higher the reward of a trajectory, higher the preference of that trajectory is going to be. Some examples of G could be just the indicator function, or classical sigmoid function, a logistic link function, or just some linear function, depending on what models the system best. And the regret objective is actually a Bayes regret. So assuming that there is a distribution over the states, they want to minimize the regret or the cumulative expected performance of the two actions, two trajectories, pi I1 and pi I2, with respect to the best policy in the hindsight. So where pi star is the policy which maximizes the total reward on an expectation, and V is basically just the expected total reward starting from state S. Their algorithm is called dwelling posterior sampling. The overall idea is they maintain an initial prior distribution over the transition dynamics and the utility model. Every time they sample two trajectories from this prior distribution, assuming those are the true distribution, and they receive the trajectory feedback indicating which trajectory is preferred over the other, and they update the posterior of this transition model and the utility model. This goes on round, and they give a Bayesian they give a guarantee of square root t, though this is not a finite time regret guarantee. This is asymptotic regret guarantee, and this is also for the Bayes regret. Moving to the next work, the Zhou et al., they actually have pretty much the similar framework. They also assume some more assumptions on the preference models. For example, their preference is still proportional to the reward difference of the underlying trajectories. And also on top of it, they assume some assumptions like strong stochastic transitivity and stochastic triangle inequality on the preference model. With these assumptions, they try to deal with the objective of finding the epsilon, like the pack epsilon delta objective, to find the best policy and the hindsight with minimum number of sample complexities. They did a dynamic recursive back propagation kind of algorithm combined with reward-free exploration and policy search and a dueling bandit framework. I'll not go into the details of this algorithm, but the main main difficulties with these two algorithms are this relies on a restricted assumption that there is a simulator which allows you to play two actions from any state action pairs of your choice, and this assumption of backward recursion that you can roll out a trajectory of whichever state you like is a bit restrictive. They also come up with some sample complexity guarantee, which are some multiplicative factor worse than the sample complexity guarantees of value-based RL. Given this, I'll just conclude my talk here. So overall, we summarized the current existing literature of preference-based reinforcement learning and why it is important. On top of it, there are various open problems, as we already see that there has not been much work on finite time regret guarantee of preference-based reinforcement learning. Most of the theoretical works depends on very restrictive set of assumptions. So maybe we want to narrow down some of the assumptions, and analyzing infinite horizon MDPs and the performance fundamental limits of PbRL would also be very interesting. So that concludes my talk, and thanks a lot for your attention. If you have questions, I'll be happy to answer it. Thank you.